Okay, today I'm going to present my research topic, that is auto-regressive model with Kalman filter for estimation of physiological tremor in surgical robotic applications. Okay. This presentation mainly consists about the motion of the human hand, the tremor characteristics, and how we model the tremor with the AR model, and then the experimental setup we used to get these tremor data and the AR parameter selection, so later real-time implementation and followed by these experimental results. Okay, let's talk about the motion of the human hand. In humans, let's consider any motion of the hand. Besides the voluntary motion, there is some involuntary motion present. The involuntary motion is due to the subject's age or his health conditions. But now we are considering about the involuntary motion present in the healthy subjects, which means this involuntary motion is due to the neural activities of the human hands, which according to the L, he defined this involuntary motion as physiological tremor, and he defined it as a approximately rhythmic, and it is having a roughly sinusoidal wave. And its amplitude is about 250 micrometers on peak to peak, and its frequency is in between the 8 to 12 hertz. Okay, its field of presence is the micro manipulation task. Let us consider the vitreoretinal microsurgeries, which consists an accuracy of 10 micrometers. Due to the presence of this physiological tremor, we get an amplitude of 100 micrometers involuntary movement, which degrades the performance of the surgery. So, in order to get a perfect or accurate surgeries, we need these engineering aids to eliminate or to predict these tremor. Okay. Let's go to the physiological tremor characteristics. The physiological tremor parameters like amplitude, frequency, and bandwidth are varies largely from subject to subject, which means it's not constant to everyone, and it is having a band of 3 to 4 hertz mainly, and it is around 8 to 12 hertz. And due to the existence of multiple peaks in amplitude, the spectral due to the existence of multiple peaks in the amplitude spectrum shown aside, it indicates the tremor is changing dynamically in the given band. Okay, this shows the FFT, amplitude frequency spectrum of various tremor signals, which clearly shows that no one is having a unique tremor signal. Okay, review on existing methods. So, since the last decade, there is a lot of research is going on to how to estimate this tremor signal. So, the first method is the linear filters. They use the linear filters to separate the voluntary motion and the involuntary motion, but the main drawback is its inherent phase delay. And then, in order to overcome the inherent phase delay, weighted frequency Fourier linear combiner (WFLC) is implemented. It's an adaptive algorithm which can estimate and predict the quasi-periodic signals, but its performance is degraded when it is having a modulated signals. Unfortunately, this physiological tremor is a modulated signal, so the band-limited multiple Fourier linear combiner is implemented. It is an adaptive algorithm which can work well with the modulated signal, but its accuracy depends upon the step size what we selected. And then a two-stage algorithm is developed to estimate the voluntary motion by using the WFLC with the Kalman filter, which is not possible to do on the real time because of its phase delay. And then the auto-regression model with LMS and RLS are also proposed, but in this paper we are trying with Kalman filter in order to improve the accuracy. Adaptive modeling of tremor. So, in this paper we model the tremor signal in the following procedure. First, the whole motion of the hand is collected by using the accelerometers, and then Since we are using the accelerometers, which consists of both voluntary and the involuntary motion, we use the band pass filter to separate the voluntary motion from the involuntary motion. After separating the involuntary motion, we model that involuntary motion with the adaptive modeling techniques, which is used as AR-Kalman filter. And then, since we are using the accelerometers for sensing the signal, we need to do the numerical integration to get the tremor in position domain. So this is the AR method. So the figure shows which is an adaptive filter having an N-tap delays, and then which is having an N waves in order to get the predicted signal. So predicted signal is given in the equation. X cap of n is equal to W transpose into X cap of n. And the predicted error is calculated by the difference between the value of the signal current sample to the predicted sample. Based on this error, we use the adaptive algorithms to correct the weights in order to get the perfect estimation. Okay. First we use AR with LMS. We all know that LMS, least mean square algorithm, is an adaptive algorithm which relies on gradient based steepest method, and its updation algorithm is shown there. And in real-time implementation, the LMS is very useful because its computational complexity is very less compared to the other algorithms. But its drawback is the convergence of LMS algorithm depends only on the step size or the conversion factor mu. But this mu is, suppose if you choose a mu as a smaller value, then the convergence of the algorithm is very small. If we choose the mu value is very high, we may not guarantee the stability of the algorithm. So in order to estimate these convergence factors and to overcome these existing problems, we switch on to the Kalman filter. Okay, AR model with Kalman filter. A distinctive feature of the Kalman filter is we can represent this one in the state space equation. So the state space equation is shown below, and then the Kalman filter updating equations are there, where K of n is the Kalman gain based on the prediction error and the Kalman gain. We are updating the filter coefficients in this method. So and moreover, the estimation of the tremor signal in real time is mainly depends upon the covariance matrix. What is the last equation shown? Okay, experimental setup. This is the experimental setup used to collect the tremor signal. This mainly consists of PSDs, position sensitive detectors, and then IR diodes. Okay, so M2S2 setup consists of a pair of orthogonally placed position sensitive detectors and an IR diode to track the 3D displacement of the tip of microsurgical instrument in the real time. The resolution, the minimum accuracy, and the sampling rate of M2S2 system are 0.7 micrometers and 98%, and the sampling rate is at 250 Hz respectively. So in this one, we collect the tip position at the centroid position where the light falls on the PSDs. From that position only, we can calculate the tremor position. So data collection. We collect the data of 5 healthy subjects and the 5 microsurgeons on performing the two tasks, the stationary task and the tracing task. In the stationary task, the subject is asked to point a single point at one place for 30 seconds. Whereas in the tracing task, the subject is asked to trace the circumference of the circle for 30 seconds. Okay, AR model parameter selection. In the AR model parameter selections, there are two important parameters we have to select. One is the order selection, and the second one is the initializing the filter coefficients. The AR model order selection, in this one, in order to accurate modeling, we need a correct order, because in AR model, if you choose a lower orders, we don't get accurately estimate the signal. Whereas if you choose the higher orders, we may get the high noise signals. So the order correct order selection is main important in the AR model. So in order to analyze the order of the AR model, we conduct a study on 5 microsurgeons and 5 noise subjects data for various orders like second, fifth, 8th, 16th, and 32nd order. So this table shows the percentage error with AR model for surgeons data and the noise subjects data. From this table, it is clear that the third order having a very less minimum percentage of the error. Okay, filter coefficient selection. Appropriate selections of the filter coefficients lead to better convergence, because in the figure shown side, the LMS takes much time to converge. If we reduce the time, we can get a much accuracy of prediction. In order to do that one, we select some specified filter coefficients. For that one, we again conducted a study and selected the filter coefficients as 2.88, 2.83, and 0.094 for modeling this tremor data. So this table shows the comparison between the AR model with Kalma and AR model with LMS with 0 initial filters and our selected initial filters, which shows an increase in the accuracy in both the algorithms. Okay, in real-time implementation, we use this experimental setup. Actually, the stylus is named as the micron, and the bottom base is the nano positioning system, which is used to measure 100 nanometers accuracy. So here the tremor data is recorded from a subject, is given as an input to this nano positioning system in 1 DOF motion, that is in the Z direction. And in this present setup, the tremor estimator is compared with the actual tremor input signal given to the nano positioning system in real time to compare the accuracy of the tremor signal what the accelerometers are reading. So after reading the data from the accelerometers, we have to model the tremor data in the real time. For that one, we bandpass the signal to separate the voluntary and involuntary motion, and then we did the adaptive filtering using this AR Kalman and use the numerical integration to convert this accelerometer domain into the positional domain, and then we again bandpass the signal to cancel the drift obtained due to the numerical integration, and then given that signal to the control signal to manipulate the position again to that micron. Okay, these are the results shown in the real time. Yeah, okay. Okay, in the conclusion, so results shows that AR model with Kalman filter leads to the better estimation of tremor in real time, and then the appropriate selection of initial filter coefficients lead to the better estimation. Okay, irrespective of the choice of initiation, AR with Kalman performing better when compared to the AR with LMS, which shows the robustness of the AR with Kalman algorithm. And in real time, AR with Kalman algorithm provides an accuracy of 92%, whereas AR with LMS presents an 86% accuracy. Thank you.
Thank you for the presentation. Are there any questions? You need only the X1 to measure the displacement. Other systems are only for the reference.
No, actually that MTS system is for ground truth. So accelerometers are performing correctly or not, we have to check, right? So for that one, we use that setup.
Did you have some compensation for the drift of the X1?
What?
Drift, signal drift of the X1.
Yeah, I use the bandpass filter to cancel the drift and the noises due to the gravity and rising temperatures.
Any questions?
Thank you.
Thank you for your presentation.